Hello everyone, welcome to day 22 of Advent of Code. Today's problem was fairly straightforward, if a bit tricky to code. Part 1 was a simulation of falling three-dimensional blocks. Part 2 was part 1, but executed n times. While there was scope for optimization, even the naive implementation finished in a few seconds, so it wasn't necessary. As always, this video has chapters so that you can skip around, and the link to the code is in the description below. Now, without further ado, let's get started. Day 22. Sand slabs. Enough sand has fallen. It can finally filter water for Snow Island. Well, almost. The sand has been falling as large compacted bricks of sand, piling up to form an impressive stack here near the edge of Island. In order to make use of the sand to filter water, some of the bricks will need to be broken apart, nay disintegrated back into freely flowing sand. The stack is tall enough that you'll have to be careful about choosing which bricks to disintegrate. If you disintegrate the wrong brick, large portions of the stack could topple, which sounds pretty dangerous. The elves responsible for water filtering operations took a snapshot of the bricks while they were still falling, your puzzle input, which should let you work out which bricks are safe to disintegrate. For example, this is some format that I don't recognize. Each line of text in the snapshot represents the position of a single brick at the time the snapshot was taken. The position is given as two XYZ coordinates, one for each end of the brick, separated by a tilde. XYZ, so it's both this brick is at x1, y is between 0 and 2, and z is 1. So this is a 1x2 brick at height 1? Maybe? Each brick is made up of a single straight line of cubes, and the elves were even careful to choose a time for the snapshot that had all of the free-falling sample bricks at integer positions above the ground. So the whole snapshot is aligned to a three-dimensional cube grid. A line like 2, 2, 2, 2, 2, 2 means that both ends of the brick are at the same coordinate. In other words, the brick is a single cube. Oh, so again, the coordinates essentially point to the middle of the cube spaces rather than to the sides, rather than to the points on the edges of the cubes. Lines like 0010, 1010, or 0010, 0110 both represent bricks that are two cubes in volume, both oriented horizontally. So the volume of a cube is... Interesting, the bricks have no height. The bricks are always one high. Thus it says each brick is made up of a single straight line of cubes. Oh, not only do they not have height, they also don't have width, really. Or rather, they have either width or length, but not both. Both represent bricks that are two cubes in volume, both oriented horizontally. The first brick extends in the x direction, while the second brick extends in the y direction. A line like 001, 0010 represents a 10-cube brick that is oriented vertically. Oh, so they can have height, it's just they only have one dimension, really. One end of the brick is the cube located at 001, while the other end of the brick is located directly above it at 0010. The ground is at z equals 0 and is perfectly flat. The lowest z value a brick can have is therefore 1. So 551561 and 021025 are both resting on the ground, but 332 and 333 was above the ground at the time of the snapshot. Why? This one's resting on the ground because it's at z equals 1, and this one is also resting on the ground because, again, it's at z equals 1, but it's oriented vertically. Because the snapshots were taken while falling, some bricks will still be in the air. You'll need to start by figuring out where they will end up. Bricks are magically stabilized, so they never rotate, even in weird situations like where a long horizontal brick is only supported on one end. Two bricks cannot occupy the same position. So a falling brick will come to rest upon the first other brick it encounters. Here is the example again, this time with each brick given a letter so that it can be marked in diagrams. Okay. At the time of the snapshot, from the side so that the x-axis goes to the left, goes left to right, these bricks are arranged like this. So A is at the bottom, A is at the bottom and it's a Y brick. Then B is an X brick and it's on the second row. C is another X brick. I'm going to call X bricks the bricks that extend in X, Y bricks the bricks that extend in Y, Z bricks the bricks that extend in Z. And we know that they can only extend in one dimension, so this is a fine way of describing them. Then D is a Y brick, so it's only one. Rotating the perspective 90 degrees so the Y-axis now goes left to right, same bricks are arranged like this. Once all the bricks fall downward as far as they can go, the stack looks like this, where question mark bricks are hidden behind other bricks at the location. Once all the bricks fall downward as far as they go, the stack looks like this, where question mark bricks are hidden behind other bricks at that location. What? So this is A. So we're looking at this one. Oh, C fell behind B. This is what this is trying to say. Because C is an X brick and it's at Y equals 2. But B is also an X brick, but it's at Y equals 0. So C will fall behind B. Okay, again from the side. Yep, C is behind B. Now that all the bricks have settled, it becomes easier to tell which bricks are supporting which other bricks. Brick A is the only brick supporting bricks B and C. Brick B is one of the two bricks supporting brick D and brick E. Brick C is the other brick supporting brick D and brick E. Brick D supports brick F. Brick E also supports brick F. F supports a G. G isn't supporting any blocks, it's at the top. Your first task is to figure out which bricks are safe to disintegrate. So this is Jenga. A brick can be safely disintegrated if after removing it, no other bricks would fall further directly downward. Don't actually disintegrate any bricks, just determine what would happen if, for each brick, only that brick were disintegrated. Bricks can be disintegrated if they're completely surrounded by other bricks. You can squeeze between bricks if you need to. In this example, the bricks that can be disintegrated are as follows. Brick A cannot be disintegrated safely. If it were disintegrated, bricks B and C would both fall. Brick B can be disintegrated because all of the things it supports are also supported by brick C. Brick C can also be disintegrated because all the things it supports are supported by B as well. The D can be disintegrated because the brick above it is also supported by brick E. E can be disintegrated because things are also supported by brick D. Brick F cannot be disintegrated because G would fall, and G can be disintegrated because it's at the topmost brick. So in this example, 5 bricks can be safely disintegrated. Figure out how the blocks will settle based on the snapshot. Once they've settled, consider disintegrating a single brick. How many bricks could be safely chosen as the one to get disintegrated? Okay, so this is a bit of a Tetris simulation in 3D and then Jenga logic to see what we can remove or not. What does the full input look like? There's a fair amount of bricks, but not that many. And I see that the numbers aren't particularly high. Like, the maximum height seems to be below 300. And the X and Y are actually pretty compact. Like, this is a fairly thin tower. I wonder if we can do anything with the fact that X and Y are so thin. Okay, so what's the plan? The plan is we parse the input. This is going to be very easy. We just have to do 2 string splits for each line. Once we have the X, Y, and Z for each brick, we run a simulation. How does our simulation work? Basically goes through the bricks from bottom to top and then tries to make a brick go down as... So we sort the bricks by Z. We can't sort the bricks by Z, can we? Because some of the bricks have height. But this shouldn't matter. No, we sort the bricks by the lower Z coordinate. Then we just go through the bricks one by one and make them fall down as far as possible. So to do this, we're going to need a data structure where we give it an X and a Y, and it tells us what Zs are occupied there, or rather what bricks are in those X and Ys. Okay, let's write it up and see what happens. We are solving this in Livebook, so as always we start by creating a new notebook. This isn't a particularly good representation for the blocks, but figure out how to do it better in a bit. It also looks pretty hard to read. Although, maybe it's actually okay in this case, because we can clearly see that this is a Y brick, for example. You can clearly see that that the second one is an X brick. Right, we have the input. But we don't want a list, we want to store this... somehow. Well, we certainly want to sort these by Z at some point, but then we're going to have to do lookups based on the X and Y. But it will be every X and Y of every brick rather than just the edges. So, say that this is called bricks. Then, for every shall we call this? We're going to need more data structures here, but first let's actually... No, I mean, we know what the data structure we need. Because we're going to say, try to see how far this one... Let's say we're going to look at this one and see how far down it can fall. And to figure out how far down it can fall, we basically have to look at 7. Yeah, we have to look at z equals 7 and see if there's anything that intersects our set of x and y's. So this is our set of x and y's, and we want to see if any of the previous pieces are at height 7. So we will need first a lookup by z. And then for every z, every piece will have a set surface of x and y's that it covers. So, and the z we care about is not just the minimum z, it will be all the z's. And why is z special compared to x and y? Because we have gravity and we're talking about falling things. So z is indeed conceptually special. So by z is, take all the bricks, we do an enum flat map. This is going to be annoying to update though. So it's going to be annoying to update. Because later we're going to have to move bricks further down, so we're going to have to update their Z positions. Be nice if bricks had an identifier of sorts. Let's add an identifier to each brick first, and then we can do more stuff. So here we do enum index. And now our bricks have a name. Let's call this ID. So we have brick 0, brick 1, and brick 2. This will be useful later. We do by Z. Take all the bricks. Enum. This will certainly be a flat map of some sort. Have a brick. This will actually be a reduce, because we are doing a map by Z. So now, we want to add to the by Z map, we want to add to the accumulator, we want to add the current brick to the accumulator at all the possible Z's. So, brick.1, brick.z2. And for once, the fact that Elixir ranges are inclusive at both ends is going to help us. Do reduce. Start with accumulator. Z ack app.update. Going to be using for update. So we update Z. If there's nothing in it, we just add brick. If there is a list, just add brick to the list. Now we can see that at height 1 we have only one brick. At height 2 we have only one brick. Really? Wait, wasn't there... No, they're going to fall down and then they're going to double up. But at the start, each of them is at its own height. However, I see that brick 6 is the only vertical brick. The only Z brick. Okay. And now I guess we do part 1, simulate fall. Simulate fall. So first off, we take the bricks and we sorted them by Z. Is that correct? Probably is. Sort with key or something. It's not, it's sort by. So we take a brick, and then we just return brick.z1. Return bricks, what do we get? Get them sorted. But this is a bit boring. Let's add an... Is there an enum shuffle? There is. Okay, and even if we shuffle, we still get this sorting, so it's fine. So also I will inspect here so that we still have our full state in front of us. Okay, we have our bricks, so this is the order in which we're going to process them. We are now going to... What? We are now going to go through each of these bricks one at a time and then simulate a fall for them. And as we simulate the fall, we are going to update the by Z table. And in fact, by falling, we only update the Z coordinate. So we're going to probably not going to bother updating the Z coordinates in the bricks themselves. We're just going to update the map. Okay, so this is going to return a data with by Z being the new by Z. Guess I don't need to do this here. Here by Z. This is going to be a reduce of some sort. With the starting by Z. Now we have to fold this one brick as far as possible. Getting messages? Okay. What do we do falling? We start by saying Z is brick.z1. We are then going to repeatedly check if the Z's lower than this. Right, so we are going to do Z down to 1. To Elixir downward the lists go. If I do 10 to 1 to list, what does this actually give us? This gives us 10 to 1. Okay, this is the reasonable thing. So here, we're going to do brick.z1 minus 1 all the way down to 1. Wait, what happens if we do 0 to 1? This is not going to work. So we actually have to have an if here. If brick.z1 is 1, then we just return by z unchanged. Else, start doing stuff. So now we are certain that because z1, so this will be at, this will definitely never be a 0, so we'll never have 0 to 1. So this is definitely a downward range. Dot find, because we are basically trying to find the first, we are trying to find the first Z where the brick intersects with another brick. And here we are going to take by Z of Z, then enum any, and other brick. Intersects xy, brick, other brick. And we'll write our intersects function a bit later. So once we found this particular Z, what do we do? Please do. So if we haven't found one, then the Z is essentially 1. So if we haven't found another intersecting brick, then Z is 1. Say this is new Z. New Z1, yes. Then it's 1. We did find something. Other brick Z, then we just return other brick Z plus 1, because if we have intersected, we have to stop above it. Okay, now we have a new Z1. Now we have to update our Z, our by Z, to account for the new Z1. So we start with by Z. Then we do what? Then we remove the brick from all of its current positions. Enum.reduce. This is brick.z1 to brick.z2. Enum.reduce by Z. And map.update by Z at Z. Used. Then we have bricks. We probably have enum delete, remove, enum reject. Yeah, this is enum reject bricks where E is brick. Beep.id is brick.id. Can we have a self-intersect here? No, we can't. But this should be fine. Okay, so we've removed it from the we've removed the brick from the existing places, so now we do another reduce by Z, to map.update by Z. This is by Z. Do this for both at the same time. Okay, so here we update the by Z of Z. Do this by Z. We run it through one map update. Then we run it through a second map update. This one is going to be at new Z plus what? Plus Z minus brick.z1. And here we add brick if it doesn't exist, and otherwise we just add brick to bricks. Do we want to update the Z? We're not going to bother. Okay, so this should be it. This takes every brick, sees if how far down it can fall down, and then Z update by Z map for new Z. This is called new Z1 in fact. Oh, we haven't written intersects yet. Let's write intersects. It's going to take x1. Let's say brick 1 and brick 2. How do they when do they intersect? Let's get confused about this specific formula. So it has to be brick1 dot x1 in brick2 dot x1 to brick2 dot x2 check if two rectangles intersect. There we go. Just copy that. So let's just blindly update this and then we'll check if it's correct. It's definitely not correct because I think we need to have greater or equal signs everywhere. So it is for comparison. It is a conjunction of 4 things. Suspicious. Okay, let's lay it out as 4 lines then. Okay, so if brick 1 is less, so it's always 1 and 2. So if x1 of one of them is less than x2 of the other, and x2 of the other is greater than the x1, so this is if they overlap in the x dimension. If y1 is greater than y2, and y2 is less than y2, oh, so if they overlap in one dimension and then overlap in the other dimension. But I'm pretty sure we have greater or equal signs here, so it should be like this. Right, what's the next bug? Line 40, something about arities. Reduce. Simulate. No, this function has arity 1 but called with 2 arguments. This can't be line 40. This is line 40. Okay, so we take the bricks, we reduce over this. This is clearly arity 2. So the 2 arguments are a number and then a big ass map. The map is clearly by Z. This 2, this shouldn't be 2. I do spec here what I get, what are bricks. Okay, yeah, this is a map, this is a list of maps. So this is a list of maps. And this reduced here arity 1. So we're looking for an arity 1 function that it's in a fold. It must be this one, but the line numbers are completely wrong. Am I missing it? No. Anyway, here, so this is by Z. Numerable not implemented for type atom. Where is this? Line 47. I should set but the enumerable what the atom type is. That looks right. Is it here? Nil. So at some point we checked. Okay, what's... So we looked up 7 and 7 isn't in the map. Did we look up 7? Because one of the things is probably at 8. Right, so this is actually map.get by Z, Z empty list. I Okay, this returned something. And now it's saying basically everything fell to height 1, which is probably wrong. Then a bunch of things fell to height 2 and to height 3, and then nothing else fell there. Did we got the updating of the Z's right at least? Because, yeah, the only to height 1, the only Z block was 6, and it continues to be there. So I do want to IO inspect this. I'd like to see the Z before and after. So before, yeah, we have a double on 6. We have a double on 6. And then these presumably intersect, so our comparison function must be wrong somehow. So which of these intersect but shouldn't have? This is... Can we write a decent visualization for this? Not really, not in the time we have available. I don't want to spend many hours on this today. So let's slog through this. These two... So this clearly did not intersect with this. So intersects XY, returned false on it. Let's just double check that. Give it two of these maps. So this is one map. This is the second map. Should return true probably, but it returns false. Is it correct? So this is on Y11 and this is on Y02, so they definitely intersect on the Y. This is from X0 to 2 and this is from X2 to 2, so these two should definitely intersect. So why don't they? X1 is less or equal than X2. X1 is less or equal than X2. And then X2 is greater or equal than X1. Then Y1 is greater or equal than Y2. It is not. Oh, so these have to be sorted, don't they? And Y2 is... So Y1 is less or equal to than Y1 and Y2. Y1 is the greater than Y2. It is. Y2 is not. Okay, so this is... We have a range that intersect. Can we just not think about this at all? Checks if two ranges are disjoint. Okay, we can use disjoint. So, new logic here. Brick 1.x1 to brick 1.x2 brick 2.x1 brick 2.x2. So if they're disjoint in the x or they're disjoint in the y, not. Okay, this looks better. Just to double check, brick 1, brick 1, brick 1, brick 1, x1, x2, y1, y2. Brick 2, brick 2, brick 2, brick 2, x1, x2, y1, y2. Okay. So now we're seeing just 1 on the bottom, 2 on the second row, 2 on the third row. Is that correct? Is it 2 on the third row? Two on the third row, two on the second row, 2 on the third row, 1 on the fourth row, and then 1 stacked on the last 2 rows. Okay, so this is probably correct. What was our question again? How many bricks could safely be disintegrated? Right. Now the question is, can we take each brick and we check to see if it can be disintegrated. So here we do IO inspect again. How do we check if a brick can be disintegrated? We go through the bricks by Z. Then we check if any of the bricks on the level above them intersect with them, and only them. Okay, so we take each brick and then we find all the bricks that intersect with it on the level above, and then we check the other bricks on the same level and see if they intersect as well. Oh, so we can do this in a sort of batched way, can't we? But do we want to do it on a batched way? As in, we can take it level by level and then compute sets of what each brick supports, and then do some set operations to figure out. But that just sounds hard. So let's instead do part 1. Count, let's call it deletable. Table. We go over by Z. We do num.map for now. Then we take a Z and bricks at the Z. Then we iterate over the bricks at Z. What do we do with it? First thing, we check to see if any of the bricks at Z plus 1 at Z1 Z plus 1 this is going to be map.get Z plus 1 default empty list. Num.any not enum any, we want enum filter. We want to know all of the bricks above that intersect. Okay. So these are supported bricks. Now the question is, how many of the bricks are not supported by anyone else? Right, or rather, we want this is actually a filter here. Now we want to go over supported bricks and check their supports, and if any of them have exactly one support, okay, we want deletable, so we want all the bricks to be enum.all, and fire brick supports is enum.filter bricks at z, then it's going to say sect xy this one and fire brick. So these are the supports, and we just want enum this can just be a count. Here we just want supports to be greater than 1 for all the bricks above. And if all of them are greater than 1, then this is a deletable brick. So this filter will select it. So this should return a list of all of counted deletables should now return a list of all of the deletable bricks. This right. So what did it actually return? Oh, and the only gotcha here is that some of the bricks are vertical. So for those, we need to do something special. We only need to do this for the topmost brick. But we can deal with that later. First off, did this work at all? So it's saying at level 1, it couldn't delete anything. Why is this here? App, filter. Guess it just returns an actual list of bricks. So it's saying at level 0, no bricks were deletable. At level 1, 2 bricks were deletable. At level 2, the next level, 2 bricks were deletable. Where is it? Here. Then brick E. What was E? So it's 2 can be deleted, 2 can be deleted, 1 cannot be deleted, and 1 can be deleted. So it's 2, 2, none, and then 1. But how do self-intersections work here? We need to check this. Is it underlined in yellow? Variable data is unused. Sure, I guess what I want to do here is say deletable, then add this to the data. Have that. Right. But here, so we look at bricks at Z. should we update the brick? So we only need to consider a brick here if we're at the highest Z coordinate for it. Not elsewhere. But we don't know the highest Z coordinate for it, do we? We kind of do because we know its height. Yeah, in fact, we should just switch to storing the height rather than Z1 and Z2. Let's make this quick change here. Okay, so we read the bricks. This is... fine. Is it fine? No, I said we want... So instead of Z1 and Z2, we will store... Z1 in height. Do that here. Let's do it here. Right, so here we're going to call this brick H. This is going to be brick of Z1, but the brick of Z2 app.put brick this actually app.put H is going to be .z2 minus brick.z1 plus 1. We add brick H, and this should still just run because we weren't using the Z's anywhere. Did it blow up? No, it says... Hold on, so by Z has a height now, yes. And indeed there's only one height 2 brick there. Now if we look at deletable, why does deletable have Z1s and Z2s? The Z1s, it got screwed over somewhere here. No, but this is where we add by Z the first time. And so okay, here we have by Z. Oh, and here we already have height. Well, for 1 we have height, for 2 we have Z1 and Z2. I should not have started this challenge hard. Losing focus already. It's not, we haven't even done part 1 yet. So here, we go over all the bricks. Z1 correct at the start here. Yes, we have a by Z there, but here we're iterating over bricks for some reason. We're iterating over bricks that are sorted in the right order. Then we reduce over by Z. But this brick here is unfortunately not in the right format. Has to be here. This is where we have to do the munging again. Okay, so by Z is now correct. And deletable is also, it also has heights. So now when we do count deletable here, we only want to look at this specific brick if we're at its maximum height. So here, really I don't want to delete a Z1. Z1 is fine, just a Z2 is bad. Here, delete the Z2, but Z1 I want to update to be new Z1. And now we should have a Z1. Come on, why do we have a Z2 again? Because I delete... Lose patience. Should not lose patience. Right, so we have a Z1 and a height, which is correct, and a Z1 and a height. The Z1 for both of the 6s is 5, of course, and the height is 2. This is fine. Now here, we only want to check, we only want to consider a brick to be deletable. So here, we only consider this brick to be deletable if we're checking the highest Z for it. So that's brick.z1 plus brick.height minus 1. Right, so for this one, we want 5 plus 2 minus 1 equals 6. So if Z is this thing, then we do all of the below. Otherwise, we do something else. Otherwise, we return false, basically. If we're at the highest brick for it, and for most bricks this is actually Z1 plus 1 minus 1, which is Z1, so it will be correct. Otherwise, it's not deletable. Z1 not found in 94. Saying that brick doesn't have a Z1. This is the height 0 brick. There. Okay, now it still does the same thing, but there isn't a logic error anymore. Okay, and now this should also be a flat map, because you only want a list of deletable things, yes. So the deletable ones are 1 and 2, 3 and 4, and 6. The question is, how many are deletable? So the answer here was 5. I'm now dreading the fact that this is probably now not actually going to work on the full, and I don't know how to debug this. Data.double length. This returns 5. Let's try this on the full example. 430. Okay, we got lucky. That's the right answer. You're 1 gold star closer to restoring snow operations. Now let's see what part 2 has in store for us. Part 2. Disintegrating bricks one at a time isn't going to be fast enough. While it might sound dangerous, what you really need is a chain reaction. You'll need to figure out the best brick to disintegrate. For each brick, determine how many other bricks would fall if that brick were disintegrated. Using the same example as above, disintegrating brick A would cause all 6 other bricks to fall. Disintegrating brick F would cause only one other brick, brick G, to fall. Disintegrating any other brick would cause no other bricks to fall. So in this example, the sum of the number of other bricks that would fall as a result of disintegrating each brick is 7. Right? So in this example, the sum of the number of other bricks that would fall as a result of disintegrating each brick is 7. So we want to compute 6 plus 1. For each brick, determine how many other bricks would fall if that brick were disintegrated. What is the sum of the number of other bricks that would fall? For each brick, determine... But we're still just disintegrating one brick at a time. Okay, so I think we just have to run our simulation. I think we need to try to disintegrate each brick, and then just run our falling simulation and see how many things fall. Yeah, okay, we can do this. So what do we need? What do we need to fix here? Well, one annoying thing is that our simulated fall here relies on data.bricks, but we're not updating data.bricks with the new Zs. So instead, let's just do it over... I mean, this is kind of shit, but let's just do it on by Z. We want map.values. Then we want to do 2 sorts here. First sort is by ID. Then we do anonym.unique. Second sort is by Z. And now this should still work. Right? Except that we're using Z2 here. I want to not use Z2 anywhere. I want to use just Z1 and height. Maybe we should just denormalize. So our data is currently denormalized. Maybe we should just normalize it so that we only store the bricks in one place. That's probably cleanest. Let's do that actually. So we're going to have data.bricks, but now our bricks are going to be... This is going to be a map. So here, where we do bricks. Instead of doing bricks ID like this, we also add IDX as a tuple, and then we turn this into a map. Okay, by Z. We reduce over the bricks. This is fine because you also have the ID in the brick itself. Then we update the brick with its height. Just do this here so that we don't have to do any munging. So instead of Z2, we have height, which is Z2 minus Z1 plus 1. Okay, now we don't have to do this crap anymore. Now we go from brick 1 to... from Z1 to brick 1.Z1 plus H. Minus 1. Then we reduce. Then we update our brick Z with just the ID. So here we have brick.id. Have brick.id. Okay. Then we do simulate fall. So when we do simulate fall, what's new? The bricks are a map, so we pull out the values and then we sort. We reduce over the bricks which are now a map, so this is like this. Brick has a Z1 and it's correct. We compute the new Z1 by going downward, this is fine. Now here, we have to update the by Z map. Well, we have to say new brick first. New brick is brick, but with Z1 is new Z1. Then we update bricks. It's brick.id, new brick. Okay, we updated bricks. Now we have to do this Z1 plus brick. Brick.h minus 1. Then we update bricks. Other ID equals brick. We remove them from the old location. And then we update z1 plus z minus brick.z1. This is unchanged. This is going to be brick.id. Some bricks. We don't do any sort of updating like this. We just do brick.id here. But now the whole thing, this is new by z, because we're updating both bricks and by z. So this is going to return bricks and by z. Here we also return bricks and by z. Our accumulator is bricks and by z. Bricks and by z. Here bricks and by z. Okay, intersects x and y is fine, deletable. We go through by z. By z hasn't really changed except that bricks at z, this is a brick ID. So our brick is actually bricks of brick ID. Have you ever looked at a word and thought this is not how it's supposed to be spelled? I'm now looking at the word brick and thinking, is this really how you spell brick? Is there really a C in there? Anyway, so we got the brick. We do the check. And the rest of this is basically the same, right? Because this is only operating on by z. So this should run and it should still output 430, which is the correct answer. Defined variable h line 24. Right, it's brick.h. Function clause matching in some anonymous function at line 41. This is new brick. New bricks. Line 41. So here is the strong. So it was given two arguments. The first argument is obviously a brick, and then the second argument is a tuple of two things. Function clause matching. The following arguments were given. Did I double up on names somewhere? Bricks, yes. Bricks. Let's just not give this one a name. No function clause matching. Same one, it's line 38 now. This is a tuple. Does data.bricks. And it gets a brick. Bricks. Is the first one the one that's wrong? Yes, there's no index. Why is there no index? Because I already did map values there, that's why. Okay, no function clause matching in intersects xy. So we gave it a what? Thing and then a number, 1001. Where was this called? This was called on 45 or 76? 76 is this, what's 45? Here. So other brick is... Indeed. Other brick is... ID. No. 91. 91 is here. Okay, so we get bricks at z plus 1, bricks at z plus 1, higher brick ID. This is actually bricks of higher brick ID. $76. But where's 96? They just fix this one. Here. No, I fixed the one above. Higher brick ID. What's bricks at Z? Bricks at Z is also IDs. This is bricks of this. Bricks of... Split it over multiple lines in a second. Better? 430, so... Okay, so now we're updating bricks correctly. Let's run this over example, let's see what our out... Let's see how bad this looks now. Okay, so we have our brick map, and our brick map is actually is ID to ID, is ID to brick, and our bricks don't have a Z2, but they do instead have a height. And then we have a by Z, which says what bricks are at each, which brick IDs are at each elevation. Okay, this looks plausible. Now let's do part 2. For part 2, we are going to try to delete every brick and then see how many bricks fall. Actually, let's do one more thing here. When we do simulate fall, let's also count how many bricks fell. Right, basically we need to count how many bricks have a new Z1 here. Where new Z1 is different from existing Z1. Let's do num fell here. This is 0. This is num fell. This is num fell, so if we're on the bottom level, then none of them fell. Then here we have new Z1. If new Z1 is different from brick.Z1, do. Something, which will be actually everything we did below. But, oh, actually, let's do it the other way around. So if new Z1 is equal to brick.Z1, then nothing fell. So we're just going to return bricks by Z and none fell. Else, we're going to do this whole thing. Then we're going to return num fell plus 1. Here we also add num fell to our data. This should run. Num fell not found, right, because here we're adding it for the first time. It's for 30 and it says 117 fell. Out of curiosity, what happens on example? It says 5 fell. Is 5 fell correct? Well, we can determine this by looking at by Z. So, there are 2 of them on line 2, so that's 1. These 2 fell over here, so that's 3. One fell above, so that's 4. And then 6 also fell a bit, so that's 5. Okay, that's correct. And the fact that num fell and deletable are the same number is just a coincidence here. Right, let's do part 2. Start by doing part 1, read input. For example. And now we are going to try to delete every single... We are going to try to delete every single brick and then see what happens. See what happens if we simulate that fall. No, first we do one simulate fall. Yes. And now we are going to try to delete each one of these and see what happens. Let's say part 2. Delete each and fall. Actually, we do data dot bricks dot keys and fall. Delete. This gives us all the keys. So now we're going to try to delete each of them. So we're just going to make a new data. Let's call it data without. This is going to be what? How do we write this? We write this as data app.update exclamation mark. We are going to update first bricks. We don't need to update bricks, do we? We don't care about bricks at all because we run on ByZ. No, we are running on bricks. Update bricks as well. Okay, bricks. And this one actually is just... we update bricks, and what do? We just do map.delete bricks f ready to delete. And okay, now we do another update. This is ByZ. This one's a bit more involved. We have to filter each level by... we have to reject from each level the brick ID to delete. So this is ByZ. A map.map or something. Guess not. It's a num.map then. fn. This is Z. This is brick IDs. Return Z and reject brick IDs. fn. So we can just say 1 equals brick ID to D. Then we turn this back into a map. So now if I run this, it should give me a bunch of data with each of these IDs removed from it. So if we look at the very first one, there should be no 0. There should be no 0, and indeed, you see that there's no 0, so this is going to fall down. And num fell. Let's also delete num fell. Okay. So this is 0 removed, then this is going to be 1 removed, and indeed 1 is removed. This is 2 removed. Yep. What happens with 6? That's the interesting one. So this one is the 5 removed one. So now when we do 6, we remove 6 from the bricks as expected, and then we removed 6 from both of the ByZs. Okay. So now we can just do simulate part 1 simulate fall. Data WO. Num fell. Here, let's just return ID to delete and num fell. So if we delete 0, 6 of them fall. We delete 1, 0 fall, 2, 0, 0, and then if we delete 5, 1 falls. Is this right? Seems right. What happens if we run this on full? We of course need to sum these up, but I'm just curious how long this will take. I mean, it took a bit of time, but not that bad. Okay, so then we just need to sum up the second element in each tuple. I assume there's a catch here that I'm missing because this seems suspiciously easy given the last 2 days. Nope, so it turns out this was just a really easy day. That's the right answer. You are 1 gold star closer to restoring snow operations. You have completed day 22. Yeah, this is weird. I guess what's going on is that the different problems on each day are meant to exercise different things, and I just happen to be pretty good at just straight up coding an algorithm, even if it's a fairly tricky algorithm. Like, there are lots of places where we could have made mistakes here, but ultimately there was nothing clever here. We just wrote the thing. It took a bit of time, and we could definitely optimize this, but there's no point. And yesterday was a very small amount of code if you could figure out what was actually going on. And if you couldn't figure out what was going on, which happened to me, then you wrote a bunch of code, but that didn't really help. Yeah, so different days of advent of code test out different things in people. What do the stats look like? Yeah, this looks... Yeah, look at yesterday. Still, over half the people couldn't solve part 2 yesterday, which is unsurprising because part 2 was hard. And then today, everybody who solves part 1 also solves part 2, more or less. But I can't tell if this number is lower than usual or not. As in, I can't tell if more people are having trouble or not. I guess we'll find out tomorrow. Okay. Preview time. Preview. So we parsed our input. Well, we went back a couple of times to make our code better, but let's just focus on the final code. So we parse our input by reading the X, Y, and Z for each brick. But then we remove the Z and we record just the height for it. This helps us with updating, because we're going to be updating the Z coordinates a lot in the future. It helps to just have one Z coordinate to update rather than two. And then we compute our data structure for quick lookups, which is an index by Z of all of the bricks that are present at that Z. So notably, this means that the same brick might be present at multiple Zs if it was a vertical brick. And as I say this, I realize that we never actually used the property that the bricks are sort of one-dimensional, as in they either have height, width, or length, but never more than one. Our code would work in the general case. Okay, then we wrote a simulate fall function that just goes over the bricks and sees, and then, where is it? Finds a lower Z coordinate. Then it checks all of the levels underneath it for bricks that intersect with it in the X and Y plane. And every time, and we basically are looking for the highest. Yeah, we are doing a downward search, and we're basically looking for the highest Z where we do have an intersection. And if we didn't find any intersection, then it means we fell to the ground, and if we did find an intersection, that means we stopped above the intersection. Now, if the new Z is different from the old Z, then we have to update the Z coordinate for this current brick. And we do that by first updating the Z1 coordinate in our bricks map, and then updating the by Z data structure by removing the current brick from all of the places where it currently was, and then adding it to all of the new Zs where it has to be, where it fell down to. And once we do this, we also keep track of how many bricks fell, which is useful in part 2. Our intersection function that checks whether two bricks intersect on the X and Y plane is really simple. It just uses ranges, and a brick intersects if it isn't disjoint on both things, on both X and Y. Or rather, if it is disjoint, or if the X's are disjoint, or if the Y's are disjoint between the two bricks, then the thing definitely doesn't intersect. That's the logic here. Now, for part 1, we had to figure out how many bricks we can delete that wouldn't cause any other bricks to fall. So we just iterated over all of our bricks. Yeah, we iterated over all the levels, and we iterated over all the bricks at the level. We found for the current brick, we figured out all the bricks that it is currently supporting, and then we checked if those supporting bricks have anything else supporting them. And if they have any more supports, then it means, and if all of them have more than one support, then it means we can delete the current brick and nothing would fall. And the only gotcha here is that when we have a vertical brick, we only want to do this check for the highest point the brick reaches. We don't want to try to delete, we don't want to do this check for the intermediate positions it occupies, just for the highest one. And then, yeah, this was just a straightforward count. And then part 2, we literally went over every possible brick, then deleted it from our data structure, then simulated the fall and checked how many bricks fell during that fall. And we can do this because we're using Elixir with only pure data structures, so it is trivial for us to compute a new data that is just like the old data but with one ID removed. If this was some sort of imperative data structure, it would be trickier to do. We'd have to first do a deep clone and then update the new data structure, or something of the sort. And that's it. That's it for today. Where's the calendar? Here. We have just done day 22. So thank you for tuning in and see you tomorrow when we do day 23.